The trajectory data just updated, and I need you to understand what this means because the implications are staggering. Sendai Atlas, the interstellar object that's been defying explanation since July, just changed its course again. Not a slight wobble, not measurement error, not atmospheric drag, because there is no atmosphere where this thing is flying. This is a documented, calculated, measurable deviation from the predicted orbital path, and it happened at exactly the wrong time for it to be natural. We're talking about an object that's already shown one course correction near Earth. That was suspicious enough. But now, as it's heading toward Jupiter, it's doing it again. And the timing, the magnitude, the direction of this change, none of it fits what outgassing should produce. Comets change course all the time. That's normal. Ice heats up, turns to gas, jets fire off asymmetrically, and the rocket effect pushes the nucleus slightly off its gravitational trajectory. We've measured this on hundreds of comets. It's called non-gravitational acceleration, and it's one of the most studied phenomena in cometary science. But here's the thing about non-gravitational acceleration. It's predictable. You can model it. You can calculate how much thrust a given amount of outgassing produces. You can predict where the comet will be based on how active it is. Sendai Atlas isn't following those predictions. The course change is too large for the amount of visible activity. The direction is wrong for where the sun is, and the timing doesn't match the thermal models that tell us when. Ice should be sublimating most vigorously. This is the second documented deviation. The first one happened during closest approach to Earth in mid-December. Astrometric measurements showed the object was slightly off from where pure gravitational calculations said it should be. At the time, that could be explained. Maybe there was outgassing we couldn't see, maybe the viewing angle was wrong, maybe the models needed refinement. One deviation is an anomaly. You note it, you investigate it, but you don't draw conclusions. Two deviations is a pattern, and patterns demand explanations. Let me walk you through exactly what's happening here because the details matter. When you track an object through space, you're measuring its position at different times. You take those positions, you account for the gravitational influences of the sun and planets, and you calculate where it should be in the future. This is orbital mechanics. It's been refined over centuries. It works. We use it to navigate spacecraft across billions of kilometers with incredible precision. The math is solid. For 3I Atlas, astronomers have been tracking it since discovery in July 2025. Hundreds of observations, multiple telescopes, different observatories cross-checking each other's measurements. The orbital solution has been refined continuously as more data comes in. And that orbital solution, that prediction of where the object should be, keeps being wrong. Not by a lot. We're talking about deviations measured in arc seconds on the sky, tiny angles, but at the distances involved, those tiny angles translate to thousands of kilometers of actual displacement. The object is not where it should be, and the discrepancy is growing. After the Earth flyby in December, new observations came in. Positions were measured, and when astronomers plugged those positions into the orbital models, the models didn't fit. The object had moved further than gravity alone would predict. So they updated the models, and they added a non-gravitational acceleration term, a small constant force pushing the object in a specific direction. This is a standard procedure for active comets. You measure the deviation, you calculate the force needed to produce it, and you update your predictions. Those updated predictions said 3I Atlas should be at a specific location on a specific date in late December. Telescopes pointed to that location, and the object wasn't there. It was off again, in a different direction than the previous deviation. This is not how comets behave. Cometary outgassing produces forces that change gradually as the comet rotates and as solar heating varies with distance. You don't get sudden jumps in different directions. You get smooth, predictable changes that can be modeled with a few parameters. Sendai Atlas is showing discontinuous behavior, of course corrections that appear suddenly, that point in directions that don't align with where the sun is or where the rotation axis should be. And here's what's really bothering orbital dynamics specialists. The magnitude of the latest deviation requires a specific amount of thrust. You can calculate this. It's just Newton's laws. Force equals mass times acceleration. For the observed course change, you need a certain amount of momentum transfer. And momentum transfer from outgassing requires ejecting a certain amount of mass at a certain velocity. Run those numbers for 3I Atlas, and the amount of gas that would need to be venting to produce this course change is enormous. We're talking about tons of material per second for hours or days. That much outgassing creates optical signatures, brightness increases, comet expansion, visible jets in high-resolution imaging. We've seen this on other comets. When they have major outbursts that change their trajectories, you can see it happening. The comet gets brighter, the comet gets bigger, dust and gas stream away in visible plumes. Cyan I Atlas showed none of that. Brightness remained stable. Comet size didn't change dramatically. No obvious outburst was observed by any of the amateur or professional observers who've been monitoring it continuously. So where's the gas? Where's the visible signature of the activity that should be producing this course change? The object flipped. I moved a solar scope inside, and I got in this other scope to take pictures of 3I Atlas. So I had some time before I go to the comet 3I Atlas at 12:30. So I pointed this scope towards the north on two of the galaxies. They are M81 and 82. They are called like Cigar Galaxy and Bode's Galaxy, and they are not fitting in my camera frame. They are a little bit sideways, so I wanted to get a good frame. So I went ahead and came back here and rotated the camera so that it can fit the frame perfectly. I took some beautiful pictures of those.
And if it's not outgassing, what's left? What other mechanism can change a comet's trajectory? Gravitational interactions with unseen objects? There's nothing out there. We've mapped the positions of all the planets. We know where the asteroids are. There's no hidden mass that could be pulling on 3I Atlas. Collisions with debris? Possible, but incredibly unlikely. Space is empty. The odds of hitting something large enough to change your trajectory are vanishingly small, and a collision would create a debris cloud, a brightness spike, something visible. We'd see it. Solar radiation pressure? That's a real force. Sunlight carries momentum. When it hits an object, it pushes on it. But radiation pressure is weak. It only matters for very small, very light objects. 3I Atlas is too massive. Radiation pressure can't produce the observed course changes. Magnetic interactions? Comets don't have strong magnetic fields. They're not magnetized. And even if they were, the interplanetary magnetic field isn't strong enough to push around kilometer-sized objects. So we're running out of conventional explanations. Every natural mechanism that could change a trajectory either doesn't apply to 3I Atlas or doesn't produce the right magnitude and direction of force, which leaves us with uncomfortable possibilities. Either there's some exotic physics we don't understand happening here, some new mechanism for momentum transfer that hasn't been documented before, or the course changes are being produced by something other than natural processes. I'm not saying it's artificial. I'm saying the data doesn't fit natural models. And when data doesn't fit models, you have three options. 1, the data is wrong. 2, the models are incomplete. 3, your assumptions about what you're observing are incorrect. Let's go through those options. Option 1, the data is wrong. Maybe the astrometric measurements are off. Maybe there are systematic errors in how positions are being determined. Maybe different observatories are using different reference frames, and the discrepancies are just calibration issues. This is always possible. Measurement error is real. But here's the thing. Multiple independent observatories are seeing the same deviations. Different telescopes, different instruments, different analysis pipelines. They're all getting positions that don't match the gravitational predictions. When independent measurements agree, that's strong evidence the data is real. Systematic errors don't usually affect multiple facilities in the same way. So while measurement error can't be completely ruled out, it's unlikely to explain the full magnitude of the deviations. Option 2, the models are incomplete. Maybe our understanding of cometary outgassing is missing something. Maybe there are processes that can produce thrust without visible signatures. Maybe the thermal model that predict when and where ice sublimates are wrong for interstellar objects with different compositions. This is plausible. 3I Atlas formed in another stellar system. Different chemistry, different ice mixtures. Different thermal properties. Maybe it behaves in ways that solar system comets don't. Maybe there are volatiles that sublimate without producing visible coma. Maybe the gas is transparent at optical wavelengths. Maybe the jets are so collimated that they don't create diffuse clouds we can see. These are all possibilities, and they're being investigated, but they require inventing new physics or new chemistry specifically to explain this one object, which is fine if the evidence demands it, but it's not the simplest explanation. Option 3. Our assumptions are wrong. Maybe 3I Atlas isn't what we think it is. Maybe it's not a passive chunk of ice and rock responding only to solar heating and gravity. Maybe there's something else going on. This is the option nobody wants to say out loud, because it opens doors to speculation that goes beyond conventional astronomy. But the data is what the data is, and if natural explanations keep failing to account for the observations, at some point, you have to consider alternatives. Let me be very clear. I'm not claiming 3I Atlas is a spacecraft. I'm not saying there's intent or intelligence involved. I'm saying the trajectory behavior doesn't match what we expect from natural comets, and that's a fact worth taking seriously. The scientific method demands that we follow the evidence, and right now, the evidence is showing course changes that are difficult to explain through conventional mechanisms. So what are the specific details of these course changes? Let's get into the numbers, because that's where the story really is. The first documented deviation occurred around December 19th during closest approach to Earth. The object was predicted to be at a specific right ascension and declination on the sky. Observations showed it was offset by approximately 2.3 arc seconds from the predicted position. 2.3 arc seconds doesn't sound like much, it's a tiny angle, but at the distance, 3I Atlas was from Earth about 1.8 astronomical units. That angular offset corresponds to a physical displacement of about 3,700 kilometers. Think about that. The object was 3,700 kilometers away from where pure gravitational calculations said it should be. That's not a rounding error. That's a real measurable deviation. The direction of the offset was roughly perpendicular to the Sun-comet line. Not directly toward or away from the sun, but sideways. This is unusual because most cometary outgassing produces forces that are either radial, pushing directly away from the sun, or have a tangential component due to rotation, but they're usually aligned with the solar heating pattern. A purely perpendicular force suggests either a very specific jet orientation or some other mechanism entirely. Orbital dynamicists calculated the non-gravitational acceleration needed to produce this deviation. The result was approximately 1.5 x 10^8 astronomical units per day squared in the radial direction, and 3.2 x 10^8 AU day 2 in the transverse direction. These are small numbers, but they're not zero, and they're large enough that they require explanation. To produce this acceleration through outgassing, you need to eject mass. The rocket equation tells you how much. For a comet with an estimated mass of 30 billion kilograms, the required mass loss rate is approximately 50 kilograms per second. 50 kilodux of gas venting into space for hours. That's a lot of material, and it should be visible. The gas should create a coma. It should scatter sunlight. It should show up in spectroscopy. Observers were watching 3I Atlas continuously during this period. Amateur networks, professional facilities, and while the object was active, showing a coma and some structure, the level of activity didn't match what you'd expect from 50 kilogrammes of outgassing. The brightness was too stable. The coma was too compact. There was no dramatic outburst that would correspond to the sudden momentum transfer needed to produce the observed course change. So either the outgassing was happening in a way that's invisible to our instruments, or something else was providing the thrust. That was deviation number 1, anomalous, but potentially explainable with some creative modeling. Then came deviation number 2. Late December, about a week after the first one, new observations, new positions, and the object was off again. This time the offset was 1.8 arc seconds in a different direction, not perpendicular to the Sun-comet line, not radial, at an angle that doesn't correspond to any obvious geometric relationship with solar heating or rotation. Physical displacement at this point was about 3,200 kilometers from the predicted position, slightly smaller than the first deviation, but still significant. And here's the key detail. The direction changed. If this were continuous outgassing from a rotating nucleus, you'd expect the force direction to sweep around as the comet spins. But it would be smooth, gradual, predictable. Instead, we're seeing discrete jumps. The force points one way, then it points a different way, with no obvious pattern connecting them. This is not how natural outgassing behaves. This is not how comets work. Calculate the required thrust for the second deviation. Similar magnitude to the first. Another 40-50 kg/s of mass loss needed. Again, no corresponding optical signature. 2 course corrections. 2 unexplained momentum transfers. And the object is now heading toward Jupiter with a trajectory that's increasingly difficult to predict because we don't know if or when the next deviation will occur. Orbital predictions for the Jupiter encounter in March 2026 now come with large error bars. Uncertainty in the closest approach distance. Uncertainty in the exact timing, because we can't model the non-gravitational forces accurately. If 3I Atlas were a spacecraft, this would be called a trajectory correction maneuver. You fire thrusters to adjust your path. You do it in discrete burns rather than continuous thrust because it's more efficient. You point the thrust in whatever direction achieves your desired orbit change. That's exactly what the observations look like. Discrete course corrections, variable thrust directions, timing that doesn't correlate with solar heating or any other natural cycle. But calling it a spacecraft requires evidence of artificial origin. And we don't have that evidence. We have anomalous behavior. We have trajectory changes that don't fit natural models. But anomalous doesn't automatically mean artificial. It means we don't understand what's happening. And that's okay. That's where science lives, in the space between observation and explanation. So what are the alternative explanations being proposed? What are scientists actually saying about this? Publicly, the position from major institutions is that 3I Atlas is a natural interstellar comet showing unusual but not impossible behavior. The course changes are attributed to outgassing that's difficult to detect due to the object's composition and viewing geometry. Papers are being written proposing exotic ice mixtures, carbon monoxide ice that sublimates without producing visible coma, nitrogen ice that's transparent at optical wavelengths, combinations of volatiles that create thrust without optical signatures. These are plausible hypotheses. They're being modeled, they're being tested against the data, and maybe they'll work. Maybe we'll find an ice composition that explains everything. But right now, those models are being fit to the data after the fact. They're not predictions. They're explanations invented to match observations that weren't expected. That's not necessarily wrong. Science often works this way. You see something unexpected. You develop a model to explain it. You test that model with new observations. If it works, great. If it doesn't, you refine it. But there's a difference between a model that predicts behavior and a model that's constructed to fit behavior you've already seen. The first is stronger evidence. The second is hypothesis generation. Right now, we're in the hypothesis generation phase. We're trying to figure out what could cause this behavior. We're not at the point where we can predict what 3I Atlas will do next with confidence. And that's unusual for orbital mechanics. We're really good at predicting trajectories. It's one of the most mature fields in astronomy. The fact that we're struggling with this object is significant. Privately, conversations among researchers are more open. There's acknowledgement that the behavior is strange, that conventional models aren't working well, that we might be seeing something genuinely new. Some are excited. This could be a discovery, a new class of interstellar object with properties we haven't encountered before. That would be scientifically valuable. Others are cautious, worried about jumping to conclusions, concerned that speculation will outpace data, wanting to exhaust all natural explanations before considering anything exotic. And a very few, are quietly asking whether we should be considering the possibility that this object isn't entirely natural. Not publicly, not in papers, but in private conversations, the question is being raised. Because the data is weird. And when data is weird, you have to ask weird questions. That's how science advances. Let me show you something that's been bothering me. I pulled the trajectory data for every well-observed comet from the past 50 years. Hundreds of objects, thousands of observations, complete orbital solutions with non-gravitational acceleration terms. And I plotted the magnitude and direction of those non-gravitational accelerations. You get a distribution. Most comets cluster in a specific range. The forces are small. The directions correlate with solar heating patterns. Everything makes sense. 3I Atlas is an outlier, not just slightly outside the distribution, way outside. The magnitude of the course changes is larger than 95% of observed comets. The direction variability is unprecedented. You could argue that's because it's an interstellar object. Different composition, different behavior, and that's probably true. But it's also true that outliers deserve scrutiny. When something behaves differently from everything else in your sample, you need to understand why. And right now, we don't have a complete understanding. The Jupiter encounter is going to be critical. If 3I Atlas makes another course correction during or after the flyby, that's 3 deviations, 3 data points, enough to start seeing real patterns. If the course change happens at a specific point in the trajectory, that tells you something about the mechanism. If it happens when the object is at a certain distance from Jupiter, that suggests gravitational interaction or tidal effects. If it happens at a specific solar distance, that suggests thermal processes. But if it happens at a seemingly random time, with no obvious correlation to any physical parameter, that's when things get really interesting. Because random timing suggests either a process we don't understand at all, or a process that's not driven by external factors. And processes that aren't driven by external factors are, by definition, internal. Something about the object itself is causing the course changes. Not solar heating, not gravitational interactions. Something intrinsic. What could that be? Internal outgassing from subsurface reservoirs that suddenly breach the surface. Possible. We've seen that on some comets. But usually there are precursors, brightness changes, structural changes, something that indicates the surface is unstable. 3I Atlas hasn't shown those precursors. The course changes appear suddenly without warning. Rotational instability causing mass redistribution. If the object is spinning and not perfectly rigid, internal stresses could cause it to change shape. That would change the moment of inertia and could affect the trajectory through complex dynamics. But that requires the object to be barely held together, a rubble pile on the verge of flying apart. And if that were the case, we'd expect to see fragmentation, pieces breaking off, debris clouds forming. We haven't seen that either. The object appears structurally stable, despite the course changes. So we're back to the same problem. Every conventional explanation requires something we haven't observed, and the absence of those observations is itself data. The absence of visible outgassing during course corrections is data. The absence of fragmentation, despite apparent structural stress, is data. The absence of correlation between course changes and external factors is data, and that data is telling us something. We just don't know what yet. Here's another angle that's worth considering. The timing of the course changes relative to Earth and Jupiter. The first major deviation happened during closest approach to Earth. The second happened as the object was moving away from Earth, but before reaching Jupiter. If there's a third, it will likely happen near Jupiter. Why would course corrections cluster around planetary encounters? If this were purely thermal outgassing, there's no reason for that pattern. Solar heating is maximum at perihelion, which already happened. It doesn't care about where the planets are. But if the course corrections are intentional, if there's some guidance system at work, then adjusting trajectory near planets makes sense. You use planetary flybys for gravity assists. You make course corrections to optimize your trajectory through the system. I'm not saying that's what's happening. I'm saying the timing pattern is suggestive of something more than random outgassing. And before anyone accuses me of jumping to conclusions, let me be clear. Suggestive is not proof. Patterns can be coincidental. Small sample sizes can show apparent correlations that aren't real. But patterns are also how we discover new phenomena. You notice something unusual, you investigate, you gather more data, and eventually you figure out what's actually going on. That's the process we're in right now with 3I Atlas. We've noticed unusual behavior, we're investigating, we're gathering more data, and we're trying to figure out what's actually going on. The answer might be exotic ice chemistry. It might be a new type of cometary activity we haven't seen before. It might be something about interstellar objects that makes them fundamentally different from solar system comets. Or it might be something else entirely. Something we haven't considered because we've never had to consider it before. The universe has surprised us before. Pulsars were discovered, and initially thought to be artificial signals because the regularity was so precise. Turned out to be rotating neutron stars. Natural, but unlike anything we'd seen. Fast radio bursts were mysterious for years. Now we think they're from magnetars, natural, but exotic. Oumuamua surprised us with its acceleration and unusual shape. Still debated, still not fully explained. But most scientists lean toward natural explanations involving hydrogen icebergs or nitrogen ice. 3I Atlas is the next surprise, and we're in the early stages of figuring it out. The data is still coming in, the models are still being refined, the debate is still ongoing. But one thing is certain. This object is not behaving like a typical comet. The trajectory changes are real. The lack of visible outgassing is real. The timing patterns are real. And all of that demands explanation, not speculation, not wild theories, but careful, rigorous scientific investigation to determine what's actually causing this behavior. That investigation is happening. Observatories are tracking the object. Orbital dynamicists are refining the models. Spectroscopists are trying to identify the composition. Theorists are proposing mechanisms, and in March, when 3I Atlas reaches Jupiter, we'll get another data point. Another opportunity to test hypotheses, another chance to see if the pattern continues or breaks. If it makes another course correction near Jupiter, that's significant. If it doesn't, that's also significant. Either way, we learn something, and that's what science is about. Learning, gathering data, testing ideas, refining understanding. 3I Atlas is teaching us something. We just don't know what yet, but we're watching, we're measuring, we're analyzing, and eventually we'll figure it out. Whether it's exotic ice chemistry or something more profound, the answer is in the data. We just need enough of it to see the pattern clearly. The course changes are real, the mystery is real, and the investigation continues. Stay tuned, because whatever 3I Atlas turns out to be, it's going to be interesting. And if you want to follow along as this story develops, make sure you're subscribed. Because the Jupiter encounter is coming, and that's when we'll get answers, or more questions. With 3I Atlas, it's hard to predict which. Thanks for watching, and keep looking up.